Hi, I'm Daniel Wilson, and today I'm going to talk about demand response policies for HPC data centers and recent work in this space by the Peak Lab at Boston University. HPC systems cover important problem spaces such as data analytics, cloud services, and scientific simulations. The current top supercomputer has peak power consumption of nearly 30 megawatts, which could translate into electricity costs of $100,000 per day. Our work in this space looks at power management policies that let HPC systems offer demand response services to a smart grid. An electricity provider needs to constantly balance electricity supply and demand. Since both of those can be unpredictable at times, some consumers can also help the grid by offering to change their demand when the provider requests changes. Data centers are well suited to offer these kinds of services because they can easily modulate their power consumption through job scheduling and software power management interfaces on servers. Of course, if you give up all power control to offering demand response capabilities, you might not be able to deliver enough computing power to keep your users happy. So, our work aims to enable that kind of participation in a way that also preserves quality of service for users of a participating data center. There are multiple types of demand response programs, but we specifically look at the regulation service programs, where changes in power usage are requested on the order of once every few seconds. These programs offer stability benefits to the power grid, as well as a chance for consumers to reduce their own electricity costs. So, how does it work? Every hour, we need to determine the average amount of power that will be consumed for that hour, the reserve capacity that you will offer. Reserve capacity is the amount of power consumption that you're willing to change within the hour upon request from the electricity service provider. So the amount of money that we have to pay for the hour of electricity ends up being the cost of the purchased power, minus some credit that we receive for offering this reserve, plus any penalties for a failure to offer the reserve, such as the cases in this example in the diagram on the left, where you see the red line indicates the amount of power that we are requested to consume, and the blue line indicates the amount of power that we actually consumed. The differences between those values indicate some amount of tracking error, which adds to the cost for the hour, and potentially, if there's enough error, prevents us from participating in future bids. The last slide covered what's called bidding, or where the consumer chooses how to participate in the market for a coming hour. This slide covers how we actually honor our bid during the hour. Throughout the hour, there may come times where the electricity service provider tells us to use more or less power. We receive these requests once every few seconds. If we're not consuming enough power, we can start new computing jobs, or we can increase power limits on servers that are already busy. On the other hand, if we're consuming too much power, we can hold jobs from exiting their wait queues, and we can decrease power limits at our active servers. But that could come at the cost of performance or quality of service of our users' computing jobs. Our recent works propose policies that help HPC systems participate in demand response programs while meeting their users' quality of service needs. We evaluate our works through simulations hosted in the MGHPCC, as well as through real system experiments on MGHPCC equipment. Our next steps are to evaluate policy efficacy with site-wide demand response participation. Please stop by the MGHPCC booth to learn more about our work with data centers and demand response.